In this video, we'll continue the skeleton notes for Unit 3, Part 1. So we'll start at this Lewis acid-base reaction example. Now remember that in class we covered Bronsted-Lowry acid-base reactions. So that starts right here. We talked about acid-base, conjugate base, these conjugate pairs, pKa's. And just before that, we talked about what a base is. Bases provide electrons to create a new bond. That is true for Bronsted-Lowry acid-base reactions and Lewis acid-base reactions. But the difference between Bronsted-Lowry and Lewis is with the acid. So what we discussed in class was that Bronsted-Lowry acids have a hydrogen atom, or we call it proton, because for a moment it exists without its own electrons. And that acid provides that proton to the base. The base uses its electrons to create a new bond to that proton. In Lewis acid-base reactions, the base is still creating a new bond with its electrons, but instead of taking an atom away from the acid, it creates a new bond to the entire acid molecule. And that requires that an atom that is part of the Lewis acid is open shell, meaning that it can accept more electrons. So boron is a common Lewis acid. We will see that in an example. Carbon with a +1 charge. Remember, for carbon to have a +1 charge, it must only have 3 bonds. Let's just say, for the sake of this example, it's bonded to 3 hydrogens. Its formal charge is +1. And it is open shell because it only has 6 electrons in its valence shell. So it can accept additional electrons, and in fact it wants to accept additional electrons to reach a closed shell. Metals are also common Lewis acids because they often exist with fewer electrons than they can hold. Another common atom is aluminum. Again, for simplicity, we'll say aluminum's bonded to 3 hydrogens. If you look at the periodic table, aluminum is in the row 3 and directly below boron. So it has similar properties to boron, where it is stable with 6 valence electrons like we've drawn here. It doesn't have a formal charge, but it can accept more. So let's go down to the Lewis acid notes, and we'll look at this reaction example here. We also call this type of reaction a complexation reaction because we form a complex. So in this example, notice in the first molecule we have boron. This molecule is called boron trifluoride. Really, what is important for the Lewis acid-base reaction is that boron is open shell. Boron is open shell. That means that this is the Lewis acid in this reaction. We know that we're working with the Lewis acid-base reaction. But in general, if boron trifluoride is in an area with another molecule that has electrons to give away, it can act as a Lewis acid and accept those electrons. The other reactant here, OH-, this is hydroxide. Notice the oxygen has a formal negative charge, formal charge of -1. It has 3 pairs of electrons that are available to give away to create a new bond. And this is the base. So we got our base here, we've got our Lewis acid. These interact with each other. Boron is open shell, it can accept more electrons. Hydroxide has electrons that can be donated, and so that is what occurs. The electron pair on oxygen, one of the electron pairs, instead of being completely owned by oxygen, it will now be shared between boron and oxygen to create that covalent bond. And over here we call this a complex, or a Lewis acid-base complex. Of hydroxide and boron trifluoride. So that's why we call this a complexation reaction. And this is generally what our Lewis acid-base reactions look like. There is an atom that is open shell, in this case that's boron, and then another atom that has electrons that can be shared with that open shell atom. Now notice, let's zoom in on formal charges here. Boron and oxygen, looking at reactants going to products, they change formal charge. Boron is neutral with 3 bonds, so if it has one more bond, like it does in the complex, it's owning, we say, one more electron, and that decreases its formal charge because electrons are negatively charged, so we go from neutral boron to negatively charged boron. Hydroxide, the oxygen in hydroxide, has a formal charge of -1. It owns those 6 electrons in non-bonding electrons, plus one more from the bond to hydrogen. Then in the complex, instead of owning those 2 electrons I highlighted in pink, it is now sharing those 2 electrons with boron, so it lost ownership over those electrons. It's now sharing them instead of completely owning them, so that increases its formal charge, making it more positive, but we're increasing by 1, which makes it neutral. It's formal charge neutral. So you can certainly use our formal charge equation to calculate formal charge of each atom, and you'll see that these changes align with that calculation. So let's talk a little bit now about curved arrows. And we are going to draw curved arrows for these acid-base reactions, but know that curved arrows are used for all reactions. They are an important, very important way that chemists communicate what happens with electrons in a reaction. Now remember that when we first introduced chemical reactions, we said this is when bonds are breaking and bonds are forming. And we said that bonds are made of electrons, so electrons are moving. That is the key part of any reaction, is that the electrons are moving around. They're being shared or not being shared anymore, going to a lone pair to a bond, or from a bond to a lone pair. Right? The electrons are moving around, and those create and break bonds. And so we show that with the curved arrows. For this reaction, one bond is being formed, no bonds are being broken. So we only need one curved arrow to show the formation of this bond. And I've already highlighted the new bond with that pink color. I'll use that same color for the curved arrow. But to show the arrow forming, to show the electrons forming the bond, we use an arrow to show that the electrons that start on the hydroxide, so I'll start the arrow over here, are now going to be shared with boron, so we end the arrow at boron. That's all we need for this specific reaction. We will certainly see reaction examples where more than one arrow is required, and we did even see that in the Bronsted-Lowry example we did in class. But let's write some specific notes about curved arrows, and then we'll do some more examples. So we as in our class, we as in chemists, we use curved arrows to show the electron movement between molecules. It's the same type of arrow that we use for resonance when we're showing electrons resonating around a molecule. When we use curved arrows for reactions, we're showing the electron movement between molecules. So this is, they again look the same, but the difference between curved arrows for reactions is that we're breaking and forming new single bonds between molecules or forming a new molecule. In resonance arrows, we're showing the possible locations that electrons can exist within a molecule, but we're not changing the nature of that molecule. So we'll just write that this is different from resonance arrows, but they look the same. And one more note to write down before we do an example is that the arrows always start at the electron source. So the start of the curved arrow, I'll highlight in yellow, is right above that hydroxide group. That's the start of the arrow. It starts at the electron source. We start at a lone pair or at a bond. The arrow shows the movement of electrons, so the arrow must start at a pair of electrons, which can be a lone pair or a covalent bond. So we start at the electron source and end at the electron. We're going to call this a sink. A sink as in another place on a molecule that is accepting electrons. The electrons can then exist there or be shared there because that molecule or that atom can hold additional electrons. So let's do another Lewis acid-base reaction example, and we'll add electrons. We will use aluminum. So let's say we have aluminum trichloride. We can already see that this element has 3 bonds only. It only has 6 electrons in its valence shell, so it is open shell. And then we'll use water. Looking at the water molecule, we have no open shell atom. Aluminum is open shell. So this is a Lewis acid. By the way, the Lewis is just for the scientists. That's why we call it a Lewis acid, scientists that first described this phenomenon. And then water without an open shell atom, but with electrons that it can give away, will be the base. So we can predict what this product will look like, but we can also think about, before even drawing it, how the acid and the base are going to react with each other. Aluminum is open shell, so it can accept more electrons. So now we look to the base and see where there are electrons that can be shared. And Those are going to be lone pairs when we're doing a Lewis acid-base reaction. The lone pair from oxygen, in this case, will create a new bond to aluminum. And so that curved arrow where I started at the electron source, that lone pair of electrons, ended it at the electron sink, the open shell aluminum, shows the new bond that is being formed. I'll note here, we call these curved arrows. They should be curved. Do not draw them as a straight line because we use that in different ways, like to show the arrow between the starting materials and products. Make sure when you're drawing electron movement, you curve that arrow. All right, so the product of this, we have aluminum with a new bond to oxygen. All other bonds remain the same. So oxygen is still bonded to two hydrogens, and it still has a lone pair that was not used. So I'll highlight that in blue here. This pair was not used in that bond, so that still exists on the oxygen. The other lone pair on oxygen is now, those two electrons are now shared between aluminum and oxygen. Then aluminum is still bonded to the 3 chlorines. So this is the structure of the Lewis acid-base complex for this Lewis acid-base reaction. We've got the curved arrow drawn in. The last thing we have to do is check for formal charges. Formal charges will arise, or a change in formal charge will arise whenever the bonding pattern of an atom changes. So looking at aluminum first, aluminum is neutral in the reactant where it has 3 bonds. In the product, it has 4 bonds, so the formal charge is going to change. It is now owning more electrons. I'll go ahead and do the formal charge calculation. So formal charge for aluminum, column number is 3, and it has 4 bonds, so it owns 1 electron per bond, and it has 0 lone pairs. So it has a formal charge of -1. So we add that charge near the aluminum. And then thinking conceptually about that, aluminum is now sharing additional electrons. It's owning 1 more additional electron compared to the reactant. So it has a -1 formal charge. Now looking to the oxygen is sharing more electrons in the product than it is in the reactant. It has 2 bonds and 2 lone pairs in the reactant. In the product, it has 3 bonds and 1 lone pair. So it's losing ownership of electron. We would expect it to become more positive. But let's do the calculation. So formal charge of oxygen, it is in column 6. It has 3 bonds, so it owns 1 electron per bond. And it has a lone pair. We're saying it owns both lone pairs. So 6 minus 3 minus 2 is +1. So oxygen has a +1 formal charge here. All right, so there is our Lewis acid-base reaction example with curved arrows. We've got this example that we went through as well, where boron is also open shell, is the Lewis acid, hydroxide is a base. And then we did add curved arrows to one example, so I just want to re-show that now that we've added language to the curved arrows. And this was for this general reaction scheme here. This was resonance, so we're going to ignore that right now. That was just an example we did in class. But in this general reaction scheme, we had the acid HA, base B, this is a Bronsted-Lowry acid. The base B, not boron, just B, creates a bond to the hydrogen with its lone pair of electrons. So we drew that curved arrow from electron pair to hydrogen, and that is this new bond. And then the bond between the hydrogen and the acid broke, and those electrons went to the acid. So I'll highlight that with this pink arrow. And now those electrons are a lone pair on the acid molecule. So here we see both a bond breaking and a bond forming. All right, I'll end the video and we'll continue talking about acid-base reactions in class.